You ever stop and think about how your phone just knows what to do the second you tap an icon? Or how your calculator spits out the right answer instantly? Well, there's this kind of invisible brain power at work making decisions billions of times a second. It's called combinational logic, and it's basically the brains behind the operation of our entire digital world.
Now really think about it for a second. How does that even work? When you type something into a search bar, how does it translate into results almost before you've lifted your finger? It all comes down to circuits that make choices based only on what's happening in that exact instant with absolutely zero memory of what happened before. So let's unpack that.
And that's the key right there. Combinational logic is all about the now. It just looks at the ones and zeros coming in at this very moment and immediately gives an output. It's a pure, stateless reaction. And that's not a weakness. Oh no, that's its superpower. It's what makes our text so incredibly fast.
Okay, so before we can build these super fast decision makers, we gotta learn the language they speak. And you might be surprised to hear it's a language that only has 2 words. This right here is the bedrock of everything digital. It's called Boolean algebra. It's really just a super elegant system of math where everything boils down to one of 2 things. It's either a 1, which means true, or it's a 0, which means false. That's it. Every complex thing your computer does is just a massive pile of these simple true or false questions.
And this is where the abstract math becomes physical reality, which is the really cool part. A 0 isn't just a number on a page. Inside a circuit, it literally means off, a state where there's no voltage. And a 1? Well, that means on. Voltage is flowing. This brilliant, super simple 2-state system is what makes every single digital device possible.
So, we've got the language down, Boolean algebra. Now we need the actual physical components that can speak this language. It's time to meet the fundamental building blocks of, well, all digital electronics.
And that's where the logic gate comes in. This is where the magic happens. A logic gate is just a tiny little electronic circuit that performs one of those basic Boolean operations. You can think of them as microscopic bouncers at a club, making a simple yes or no decision. And when you string millions of them together, they can do incredible things.
Let's start with the strict one, the AND gate. The rule is simple. The output is on, or a 1, only if input A and input B are both on. Think of it like this. You've got 2 light switches on the same wire, one after the other. You have to flip both of them to get the light to come on. That's an AND gate.
Next up, we've got the more relaxed OR gate. With this one, the output is on if input A or input B is on. It doesn't need both, just one of them is enough. This is like having 2 light switches wired in parallel. You can flip either one and bam, the light turns on.
And finally, the simplest of them all, the NOT gate. You'll also hear it called an inverter. It does exactly what it sounds like. It takes one input and just flips it to its opposite. A 0 goes in, a 1 comes out. A 1 goes in, a 0 comes out. Simple as that.
Okay, so we have our basic gates. We could just start stringing them together to build whatever we want, right? Well, not so fast. In engineering, you see, just making something work is only half the job. The other half, the more important half, is making it work efficiently.
And this is why it matters so much. Simplifying a circuit has massive real-world payoffs. I mean, think about it. A simpler circuit uses fewer physical parts. That means it's smaller, it's way cheaper to make, and it sips power instead of guzzling it. Plus, it's faster because the signal has less distance to travel. It's a win-win-win-win.
But how do you take some big, messy logical equation and clean it up? Well, you could grind through a bunch of algebra, or you could use this incredibly clever visual tool that engineers came up with. It's called the Carnot map, or as everyone calls it, the K-map. It's like a Sudoku puzzle for circuit design.
So let's look at an example. Check out this Boolean function. It's a bit of a beast, right? Now, you could absolutely build a circuit from this equation. It would work, but just look at it. It would need a ton of different gates all wired together. It'd be big, slow, and power-hungry. We can do way better. The first thing we do is plot this function onto our K-map. Each little box in this grid represents one of the possible combinations of our inputs, A, B, and C. For every term in our original equation, we just find its box and pop a 1 in there. We're basically just creating a visual map of every time our function should be on.
Okay, now for the brilliant part. The rules of the K-map let us group any ones that are next to each other. The only catch is the groups have to be in powers of 2. So, groups of 2, 4, or 8. The whole point is to cover all the ones using the biggest groups you can possibly make. So, you see this big block of 4 right here? We'll circle that. And then we can grab these two as another group. Notice how they overlap? That's totally fine. By just drawing these circles, we are visually getting rid of all the redundant parts of the equation.
And after we do that simple visual exercise, get this, that huge complicated mess from before, it boils down to just this, F equals A or B and C. It does the exact same job, produces the exact same output every time, but this version is smaller, cheaper, faster, and way more efficient. That is the incredible power of simplification.
All right, so now that we have these efficient, simplified circuits, what can we actually do with them? Well, this is where we zoom out from individual gates and start building bigger, recognizable components that perform really useful tasks.
Let's start with a multiplexer, or just MUX for short. Its job is to be a data selector. The best analogy is a train dispatcher at a busy junction where, say, 4 tracks are merging into one. The dispatcher uses a set of switches to decide which one train gets to go on to that single main line. A MUX does the exact same thing, but for streams of data.
And here's a component you absolutely see every single day, a decoder. It basically does the opposite of a MUX. It takes a short binary code as an input and turns it into a specific action. The perfect example is the circuit that runs the numbers on your alarm clock. It takes a 4-digit binary code, and based on that code, it knows exactly which of the 7 little segments to light up to show you the number 8 or 3. That's pure combinational logic right there on your nightstand.
And this quote really sums up everything we've talked about perfectly. Combinational logic is all about the now. Its output is an immediate, predictable reaction to what's coming in, and it's completely independent of anything that happened even a nanosecond before.
That statelessness, that lack of memory, is its greatest strength. It's what gives our devices their incredible speed, but it's also its one big limitation. So that leaves us with a really fascinating question, doesn't it? What if a circuit could remember? What if its output depended not just on the present, but also on the past? Well, if you could do that, you'd have the key to creating memory. And that is a topic for another explainer.